And welcome back. So what we learned in the last module? We talked to RNN about the architecture in a simpler way. And within the simple RNN, we talked about just the architecture. And then we even practiced with keras. Now, more importantly than that, if you think back to what we did in the last module, we were able to calculate a lot of performance in our modeling. So at the end of the day, what we're going to do is we're going to dramatically improve performance by minimizing the amount of ROS, and then we're going to increase predictive performance. So here's what you're going to be doing today. So I'm just going to put a little bit of a theme here. We're going to make an RNN structure that's basically one layer at the end of the day. So here's what we're going to do. A few of us parameters are actually good. It's hard to calculate when there are so many of us. We use a fewer parameters to get the best performance. The best performance in terms of deep learning or machine learning. That's why we're doing this. How to achieve the best optimal with performance the least amount of effort is something that we're going to be very interested in. And I'll delete it. So let's take a look at how 256 units worked. Compared to the ones we implanted, there are fewer rushes, has improved performance. Now, let's talk about the number of units that I just brought keras in. Now, you guys are actually going to have to bring you'll notice that right now, in precision, under simple, I'm going to stick with what I had before. Now, the parameter that you should be changing during your practical exercises is the so-called green parameter. That's right. So the truth is, the structure of the tinters in keras is the same. As long as you know the structure, how can we use the parameter? But we need to know what each parameter means in order to make good adjustments. You like music, right? If you have good hearing, you can make it sound like an optimer music, but it's different in hip-hop. It's different in classical music. It's different in dance. Equalizing isn't always the same. It depends on the genre of music. When you adjust the genre, the yin-yang technician adjusts the equalizer, controls the buttons. He knows the fine tunes. He adjusts the best fittings to the music. I'm telling you that that's how you can become an AI expert. Let's take that parameter and let's make it the best it can be. This is the definition of modeling, the optimers, that many researchers want to do. We have about 34 units. Actually, there were 20 units. ROS was taller when we had 20 units, but we only had 34. It's because I increased it 12 times earlier. I didn't double it. So I'll double it by 1. Now, I'm going to add several layers of water-cooled food network. It's a multi-tier system. Instead of a threshold, it's a multi-tier system. So what we're going to do is we're going to take that layer of output, that layer of circuitry, and we're going to make sure that we're connecting it to the next layer. And we're going to stack it up. That's how you implement it. But here's what you need to be careful of. The output of the tier connected to the next tier isn't the last one, but it signals to the next tier every time. So if we don't adjust it, right now, in keras, they use the last one. It's a multi-layered layer, so keep going until you add layers. We need to let them know that this is the middle layer, not the last layer. In order to do that, we used a sequence or a pulse is what we call the default value. Now, here's the thing. When you return something from modeling, if you return it and say the sequence is second base, it's going to go back to the next layer and it's going to go like this. Let's move on and move on. At the very end, if you don't use tools, you'll understand this as the last layer in Keras. If you look at it in code, I did that, and look. There are so many layers. It's a sample from RN. It's a simple 2. Simple arena 3. There are 4 simple lines. You have a pile of 4. But when you did the gift, he asked you to summarize it for him. The parameter has shrunk now. The parameter was something like 60,000 or so earlier. At the end of the day, the reason it shrunk is because the units have shrunk. I've narrowed it down to 34 units, instead of 256, so if I multiply m by n, down to 8,297. So we're going to hey. What was the topic? We're going to reduce the parm. You succeeded in reducing it. Let's move on to the next one. Let's look at the schematic. We have 4 layers now. 4 layers. We fought with 4 layers. If I were to illustrate this in a way that you can understand, the code is much more like this. Since you have to imagine it in your head, the layers build up like this. The first layer is stacked up here. And to summarize each layer, there are 2, 3, and 4 layers. It's like you're stacking the burgers in parallel. Patty 1, patty 2, beef 4 patties. Seasoned nuts. Now, you'll see, but for each one of them, on the RNN class is actually, if you look at it, it's just repeating what's happening right now. We'll go to the next one, and you'll notice that the parameter was 34. And then we'll say, well, the weight is basically the same. So it's 3 times 3 times 3 is 34. And that's the array of 34x 34. So that's the vector. That's why we use vector maths. You go like this and you go over. You go up like this, and then the weights go to the next layer. And then when you go to 3, you go back and then you go back. So you're doing math. When I did that, the parameter ended up looking like this. When I went back to the top, it decreased like this and decreased like this. If you look at the output value, in the end, the total parameter was reduced to 8,297. In the thumbs up window, so we need to talk about why it was reduced to 8,297. So we have tier 1, which is the first, which is the class. In the first class, we specified that hyperparameter as 34. So it's 34 times 34. So you do the math. 34 times 34. Now, the next tier. We're going to move to 2. So it's roughly 1,000. If we move to 2, 3, 4. It's actually the same structure. It's the same calculation method. It's the same structure. But it's the same input method because this is for demo games. We're going to say that the tier below, we're going to say the previous tier. 34 units on the previous tier. Basically 34 units that you have right now. On each floor, there are 34 specified. Units. But on the second floor, there are 34 units on the first floor. We're connected. And the circular energy is calculated by 30 so years, 34 times 30. So if you calculate that, you'll have 8,297 altogether. Now, you need to understand that we can calculate it that way. Now, the important thing is that the code over there calculates the calculation. So it's not rational to question whether the calculation is accurate. A human and a calculator. But anyways, if the input wasn't wrong, the algorithm would calculate me. Are there 8,000 of these? Let's move on to the multi-tiered structure. We'll test your predictive abilities. During the verification, we make predictions and based on the training data. Y. That's why we compare it to Y. It's the same as before. So in the end, what we do is we say Y and Y hat, which in Korean is a prediction value. No, we can compare the actual value and expectation. And the more this matches, the better the performance will be. Let's do the same. This is the same code that we calculated, not earlier. If you look at it now, I used the same epoch for 300. If you look at it now, I used the FCO. You're going to have to bring up a ruler and do that on Impulton. Bring up WebFlora. I'm going to look in the library and I'm going to say, show me the value of the Roth. And it's going to be the Roth on the left. Exactly. On the left, you can see how well Ruth fell from the value of Ross to the value of Epoch 300. So on the right-hand side, we're looking at Y hat. I want you to show me in the scatter plot right now the so-called Y shape, because I don't know which one is the Y shape. It's the same value as whether the X is Y or the X is Y. And the Y is Y and the Y is decreased. Anyway, it should come out diagonally and straightly. But I'm showing you what you did. In the previous episode, this is just one layer of what we've done in the previous time. It's a single layer in RNN. It's not an enumeration. It's what the layers do. But the unit did 266 months. So we had 66,000 parameters. A lot of convenience. So that's how that came about. You can see right now. I'm just going to draw a picture for the Ross value. And now I'm going to do a Y and a Y for that. Calibration flat. This time, it's the same as FCO, but they only used 34. So they have similar capabilities. This looks good too. In conclusion, oh, come on. It's 12 times as much for each of the 20 items. And 1.3 times more for each of the 20 items. The accuracy is similar. Which model would you choose? Less parameters, but Ross doesn't lose. This is a good model. We can't be sure. If we just look at the call as a picture, the way we test this in quantification is by checking the numbers. So we named the J model multi-layer. Let's check the model Friedrichs Nunwave array. Print it out. So if you go ahead and code that now, 10.2, 10.3, and then what you'll see is sequence 10.5. So that would be the actual value. And then after I do that, if you go ahead and print that out 10.20, it's 10.20. So there's a huge difference. But I'll show you J's difference again. The first 20 we did when we put the unit in. Back then, it was 9.29. That's why it's very similar, not 10.5. And the prediction was different. But it has decreased considerably. Right, it has decreased. But of course, The ratio is a little bit better than the 256 units that we used before, which was 10.42 for 266 months. So it's actually closer to 10.5. Even so, we only used 32 of them. So this is a big improvement. It's prettier than the first 20. But there are several layers. The layer is next, and the same goes for the bottom one. If you check again, it should be 10.40, but the actual value is 10.36. We can see that it's a little better than when we used 20 of them. What do you think? In the end, we've done some simple exercises. But if you compile them, you'll be able to control the units in RN. If you increase the size of the units, the accuracy will increase. It's a hyperparameter, but if you increase the size of the units, yes, because it's the number of units times the number of units. It's exponentially bigger. It takes a long time to calculate. And it's okay for the model to want us all to go to school, but it's not okay for it to take a long time. That's part of the problem. Think about it this way. We have to check the license plate, but the accuracy is 0.001, so it takes 10 minutes to check the license plate. You have to think about whether that model is a good model. But that's not all. It's a sample layer. But if you add this layer, even if you add fewer parameters, you can see that the calculation accuracy is very high. I'll stop here for the time being. In the next class, I'm going to talk about something very important we'll cover in the next class. Is that the recurrent neural network has been a very good deep learning model for data with a lot of clock sequences. But in order to overcome that threshold, a more advanced model like LSTM, which mimics human long-term memory, was created. Now, in order to understand that, the limitations of the RNN model. So next time, we'll look at situations where the limitations of the model at the bottom seem useful, but the model at the bottom doesn't work. That's all for today. I'll see you next time. Bye-bye. To all of you who broke free from the bonds and constraints of the world of transference and found my happiness, please be happy.